podcast is brought to you by LMU Munich.
Start by thanking the organizers for this wonderful conference. I'm going to discuss mainly 2 or 3 works that are soon to come out that are in the same, or rather spin-offs of the same general direction that Andy was talking about. But the first 2 that I'll mention pertain more directly simply to new features of quantum field theory in interesting space-time dependent backgrounds that we uncovered in our approach to that problem. And if I get there, I'll discuss a result in our approach to the problem of holographic Disinter, in which we find an interesting statement about the holographic RG for Disinter space. Okay, but let me begin with the first topic. No, I should say that this is all work done in progress with these wonderful young people, Xi Dong, Bart Horn, and Gonzalo Taroba. Okay, so for the beginning of this talk, I want to consider deforming ordinary quantum field theory with couplings which depend on a spatial or temporal direction x as a power law over a wide range of scales. We don't need to take that all the way to x equals 0, but let's consider it for large values of x and a wide range of them. I'll be more specific about that later. So as you can see, just by power counting, this changes the engineering dimension of the operator and couplings in this term in the perturbed Lagrangian. So it will affect whether the term dominates at large values of the coordinates and coordinate differences in observables. What we'll find, first of all, and actually this hasn't come out yet, it's something that I want to share with you here, is some novel fixed points under such a rescaling of all the space-time coordinates that one obtains from this that is a generalization of the small epsilon Wilson-Fisher fixed point, but one where we can stay in a physical dimension, just an integer dimension, and obtain a fixed point under this scaling using instead a small parameter kappa here, rather than going to a fictional dimension. This is a fun example, partly because it applies in very minimal quantum field theories. We don't need any large N expansion or supersymmetry or any of the usual crutches that we know and love. Secondly, we can ask given that these terms these couplings can affect which terms dominate at long distances, we got interested in the question of how that affects unitarity bounds, which usually restrict the content and dynamics of field theories at long distances. And we found an interesting result there, so I'll try and share both of those with you, depending on how the time goes. So let me start with the first one, and because it's so simple, it should be something that I can actually explain in real time here. So take the kind of Lagrangian that I mentioned, let's just for regulation purposes, put in the 4 minus epsilon and consider phi the fourth theory in what will ultimately take to be 4 dimensions with this kind of coupling. But before I get to the non-trivial coupling, let me put it to 0 and review briefly for you the famous Wilson-Fisher paper on critical exponents in 3.99 dimensions, where because one considers this epsilontic shift of the dimension down toward 3, the coupling becomes classically relevant. So there's a term in the beta function which is negative leading order, and at 1 loop and higher you get the usual 4-dimensional beta function. The 2 play off against each other to produce formally a nice fixed point, lambda star at 16 pi squared over 3 times epsilon. And as a formal exercise, this is very useful. It can even be pushed toward 1 using the epsilon expansion resummation techniques, as well as more recent ideas that people are exploring. But as a perturbative thing, it's got this formal character that it involves a fractional dimension. So now let's turn on this kappa, which appears here in the interaction, and see what happens. Well, kappa also affects the classical scaling dimension of the term, and ultimately what that will do is introduce a similar contribution to the leading beta function, now with kappa playing the role that was played before by by epsilon. So one can establish that, it's keeping both parameters in the game at first and looking at the non-trivial one-loop correction to the coupling and hence to the beta function, and up to corrections that turn out to be perturbatively suppressed in our fixed point that we will find. One can obtain a result for this contribution, which has the space-time dependent coupling squared sitting out front and the usual logarithmic contribution continuing to appear. So in other words, the bare coupling, if we used old-fashioned techniques, lambda tilde naught takes this form where you have the usual mu to the epsilon out front, a classical dependence on kappa, and then this one loop term with the usual pole. So imposing that bare coupling knows nothing about the scale mu that needed to be introduced, we obtain a beta function, which, as I tried to anticipate, has in it, well, the usual minus epsilon lambda, if we leave it in there, but also from this kappa that affected the classical scaling, one has this piece. So we can take epsilon to 0, keep this kappa. There was, to leading order in a further expansion in the space-time dependence of this coupling. If we ignore further dependence on that, and I'll say more about that in a moment, one has at one loop order just the usual lambda squared term, leading to a fixed point value of the coupling under this rescaling of all coordinates at once, which takes this value. So in this sense, this kappa has been traded for epsilon. Now, having broken translation invariance, we open the door to the whole function's worth of renormalizations, and of course that's important here. But in this exponentially wide range of scales, they don't matter. So this kappa we can consider to be very, very small, at which point you can see that all of this residual x dependence that I left out when I wrote these constant terms is negligible. So without any tuning beyond what you usually do in scalar field theory, you get an approximate fixed point meaning over this exponentially wide range of scales. One can go further, and if you want to tune away all of the extra operators that you generate, you can show that you can. Formally, there are beta functions for each of the space-time dependent corrections that you can generate, and if you work them all out, one finds that you can solve those equations to find a 0 iteratively. So you can always, in this expansion that I've written, solve the nth lambda in terms of the previous lambdas to find a fixed point. So it can be an exact statement, but we find more interesting the untuned example with this exponentially wide range of scales. So this is a very simple mechanism, and the idea is clear and generalizes to any quantum field theory with a marginally relevant or irrelevant coupling. We could do it for QED and obtain a similar expression for the beta function that has a fixed point. And then if you look at the force between charges and you put the coupling alpha at that fixed point value, then the potential between charges very physically scales, even though in usual QED there's a logarithmic obstruction to that scaling. One can change the signs and do it for marginally relevant couplings. One can go to d equals 3 and do this for the 5 to the 6 sorts of theories, which are important in critical phenomena. One can play with the same thing in 2 dimensions, where sigma models provide interesting examples of marginally relevant or irrelevant couplings, depending on the sign of the target space curvature. So it's a pretty general thing. One can even consider strongly coupled examples, even though it's at heart a perturbative mechanism. One could consider strongly coupled examples too by starting with some CFT, adding in conformal perturbation theory such a lambda of x times a marginal but not exactly marginal operator, And again, one finds a similar structure. So, this happens in, again, minimal field theories. We don't need large NF or large NC or SUSY. It's something that, as I said, pertains in classic theories that were studied early on in critical phenomena, and one could generalize those if one wanted to test this, although the field theory is pretty clear. So we find this a lot of fun. We haven't proposed a killer app for it yet, but it just seems like an interesting structure. The next thing that I want to discuss regarding time-dependent quantum field theory is related. It's what happens when we consider an operator with such a coupling such that this makes the operator relevant when it otherwise would not have been, when, say, it might have been irrelevant. So this therefore changes the long distance, the infrared physics of the theory. And one expects that this should be consistent with basic principles like unitarity, and it turns out to be, but in an interesting way, in situations where it might have not been obvious initially how that works. So we worked this out very explicitly in a simple set of examples based on double trace flows in large N theories, where you can just calculate everything and be very clear. So again, the idea is we have these space-time dependent couplings. They can change whether a term is going to dominate long distances or not. And let's see how that affects unitarity. So as I said, let's do this in the case of large N double trace flows, where one can calculate, for example, the two-point correlation function of a scalar operator simply by mixing between, say, some auxiliary phi field here and this operator O. Everything else, including non-adiabatic effects if we do the time-dependent case, are down in the large N expansion. So, this is trivial to compute and see what happens. In these sorts of flows, let me remind you what happens in the static case. So as usual, we consider two types of operators with dimensions delta plus and minus, d over 2 plus or minus some parameter nu. And basically, if you do a flow in the static theories, adding a double trace, say O plus, it flows to O minus, but in the range where this is irrelevant, of course, it flows to O minus in the ultraviolet, and one can calculate the correlation functions which reveal that very explicitly. So if one takes this theory with O plus, adds it to the Lagrange's double trace term, it's an irrelevant perturbation, and it basically is giving you the flow from O minus in the UV to O plus in the IR. And in that example, if this parameter nu is big enough, it's not unitary in the UV, so it has to be UV completed in some other way. So the puzzle is, what if we do that in the case where we suddenly made this operator relevant instead through this kind of space-time dependent coupling? So we still have this O plus squared, but we've made it relevant with this T to the kappa. And the upshot is that one can analyze this, and even though it involves the same thing that would induce a flow between O plus and O minus, which was not unitary in the usual theory, and which went to the UV in the usual theory, here everything goes the other way. This dominates in the IR, and when it does, one can check unitarity, and it works in a fun way. So here's the correlation function that we were talking about in this generalized theory. We can get it, given that this term dominates, simply by temporarily absorbing the coupling into the auxiliary scalar field and calculate the two-point function explicitly. So here it is, and it has these two features which basically cancel out in the condition for unitarity of forward scattering. A nice physical way of analyzing this was introduced in this paper, which we used. And this correlation function has two properties that, as I say, cancel out. There's a delta minus here in the denominator, which by itself would lead to a violation of unitarity. But there's also a minus sign in the coefficient. And the only applicable condition for unitarity in this theory, which is this forward scattering process gives a net positive answer basically because of a product of this -1 with the delta minus minus the usual unitarity bound. And so, this sort of had to be true. If the theory is well defined at some scale and you go to the IR of that scale, it should make sense. And it's interesting to see how it is that it did that. Okay, so our original motivation for this actually was the more ambitious study of duals for cosmological backgrounds. And our approach to this has been simply to take ADS-CFT dual pairs that we know and love and add stuff to them that make them into cosmological solutions and try and interpret the result on the field theory side. So a simple case we can take, a relatively simple case, is the classic case of D3 branes probing the tip of a cone with flavor PQ7 branes, let's say. And there, for a sufficiently small number of them, you get an ADS solution describing an interesting class of CFTs. But above a certain number of these flavor branes, you don't get an ADS solution, but you do get, because the potential here gets uplifted in this way that I've sketched, you get some time-dependent solution, which involves a rolling scalar field. And one finds still a warped metric, one with various properties that we explained in detail in some papers, that contains a highly redshifted region toward its infrared, but not an arbitrarily high energy region. In any case, the crossover between the number that produces the ADS solutions and the number that doesn't is something one can relate to unitarity bounds coming at it from the lower side, from the static side. And so what happened was we wondered what this number meant in field theory, and it seems to be the case that if you violate this bound, you don't have a static solution, but you do have a time-dependent one. And as we just saw in a simpler setting, time-dependent couplings can reestablish unitarity in cases where it would have failed for the corresponding static theory. So that's where that was coming from. And this is a good place then to transition to the last topic that I mentioned. How are we on time? Okay, perfect. So as I said, our approach to this problem of how to obtain a framework for cosmology, a holographic description of de Sitter space and its decays, is rather pedestrian. We consider ADS-CFT dual pairs that we know, and we add ingredients to produce de Sitter space or just rolling scalar FRW spaces such as the one I just described. The original observation that we made with Karch and Tong and others is macroscopically that the de Sitter static patch plus a bit more is covered by a metric which exhibits two highly redshifted regions. So one can write the metric of de Sitter, the part that's observable, as sine squared of some radial coordinate times the metric of the lower dimensional de Sitter in terms of this radial proper coordinate W. And so there are two highly redshifted regions which in themselves have a right to a low energy effective field theory description, very weakly coupled to what a surviving lower dimensional gravity, surviving because for the de Sitter case the warp factor doesn't go all the way up to infinity. Now, so that's all macroscopic. Microscopically, we went through a construction of de Sitter space based on the D1, D5 example of ADS-CFT. So this is three-dimensional de Sitter. It's of no phenomenological interest, but it is, I think, the simplest construction of metastable de Sitter we have in string theory, and it involves the usual sorts of procedures that we need. We have the ADS potential energy, which involves curvature played off against flux, and we need to overcome the curvature energy, add some orientifolds to produce this dip in the potential, and we still have flux. And in so doing, you can track what happens to the ADS-CFT brane construction, these color branes probing the tip of a cone, and ask what happened to that structure. And what happens is, for reasons that take a whole talk to explain better, is that the cone becomes something like this rugby or American football shaped object. The radial evolution that produces the cone turns into this, this geometry for a very simple reason having to do with the structure of the potential, that the curvature term that provides the leading force in ADS Freund-Rubin solutions has changed sign. There's a second term, and putting those two together induces radial evolution that does this instead of that. And this top picture is a microscopic realization of this earlier macroscopic observation that Disinter has two low-energy effective field theories involved in its description. And having done this microscopically, it gave us a parametric estimate of the Disinter entropy, which we interpret in a very pedestrian way as the number of degrees of freedom that are going to be needed to reconstruct the static patch. So there's a lot more details needed there. This slide is meant to sort of orient you toward various proposals for Disinter holography, one of which we heard about this morning from Andy. The one I'm discussing stays within a causal region, so it's less confusing from the point of view of the philosophical question of who can observe it, as well as having a dual description, which is ordinary Lorentzian field theory. The number of degrees of freedom is real and positive. The scale direction is the one that emerges. However, like with different gauges in field theory, it's the sort of thing where some things are manifest and others are not. And certainly in our framework, the symmetries of the global Disinter space are not manifest at all. However, we've been having fun with that. It's then an opportunity for our approach to explain that better. And we've asked simply the following question. In this description of Disinter, again, we're sitting inside a causal region. This is our metric, and it does not at all manifest the conformal symmetries of Disinter space as a whole. And again, the dual theory here lives on Lorentzian signature Disinter in d-1 dimensions. However, it's dual, of course, to a Disinter geometry in the top big D dimensions, which means the moduli have been fixed. And in ADS CFT, the fact that you fix the moduli is basically the statement that the beta functions have canceled in your dual field theory. So in Disinter, we, of course, also at least metastabilize the moduli. We look for solutions where dV equals 0. And so in our Disinter correspondence, we can ask, how is this simplification that V prime equals 0 manifested in the dual field theory? So we ask ourselves this question in the context of the holographic renormalization group. This is a the subject has a long history. There's a paper of Heemskerk and Palczynski which makes many points clear and gives a framework that we use. The idea is to start in the UV, integrate out degrees of freedom that correspond to the least redshifted region of the work factor, the ultraviolet, down to some fixed radial distance L. And having done so, one can derive a Hamilton-Jacobi equation for the Wilson action corresponding to the field theory under this RG prescription. So long story short is that in a very simple way, in this formalism, one can show that the statement that V prime equals 0 leads to a scale invariance of the single trace part of the Wilson action in the dual for both signs of the stable or metastable cosmological constant. So regardless of whether the potential has a local minimum that's negative or positive, one gets this result. So it's true both for Disinter with Disinter slicing and also ADS with any slicing. So that's the special thing about Disinter space that can be also understood in this framework within a static patch where the symmetries are not immediately manifest. Finally, one might ask in that same framework, what about the metastability of Disinter? And that has an interesting consequence as well. So in this procedure, one is of integrating out the high energy degrees of freedom of the dual theory. One is essentially computing a radial analog of an evolution from the UV to whatever slice we want to talk about. And semi-classically, one gets contributions from the constant solution, but also from other solutions of the equations of motion. And if the potential is metastable, then there are additional contributions to the wave functional that you generate by integrating over this region. I should have said what these variables are. So one integrates from the UV down to some slice and puts the fields at some value phi tilde there. That's what this quantity is supposed to be. And it gets contributions that include essentially the bound solution and analogs of it, which will contribute to the Wilson action at an exponentially small level. So these will be non-perturbatively suppressed contributions. And because of the usual single negative eigenvalue, they'll be imaginary. This, we think, is reflective of the fact that Disinter does decay if the potential is metastable, as it is in all known constructions, in string theory at least. And so at least the whole structure seems to be internally consistent. It sees the seeds of its own demise, but when it should, at a non-perturbatively suppressed level. At that point, of course, the theory decays to something more like the rolling scalar solution that I mentioned earlier, and that has its own holographic description. So let me just summarize. So we started by considering various simple results in quantum field theory modified by mildly time or space-dependent couplings, showing how that affects infrared physics, gives us a new classical contribution to the beta function under rescaling of all coordinates that leads to new fixed points, and also shifts unitarity bounds in the right way to maintain that principle. And secondly, I discussed the RG structure of the DS-DS correspondence, finding that single trace couplings don't flow. So let me stop there.
When you had your little rugby ball, was the direction of the holographic of the RG flow becoming time-like in that region?
Well, so this rugby ball is the analog of the cone. So the cone, the cross-section of the cone is like the analog of the S5 or the S3 in D1, D5. And so this is, before you include the back reaction of the color branes, which produce the flux and give you the maximally symmetric solution, this rugby ball is the analog of the cone. And so I'm just trying to explain, first of all, what the dimensions were, since I didn't really cover it. So this is an internal direction, and the horizontal here, as here in ADS, is the radial direction. So the RG flow that one would consider in these examples would be like in ADS CFT. So these color branes sit here and describe the low energy physics of these dual field theories in the usual way, and they can be deformed by relevant perturbations and so on.
Space is expanding in the vertical direction, right?
Space is expanding. Yeah, I mean, space. The time isn't depicted here, but yeah, space is.
But the RG flow is in.
It's in the radial direction.
In a direction where space is not expanding.
Yeah, the holograph. The scale direction is this W direction here, which is a spatial direction.